Okay, okay, okay. With this, we'll move on, and now we'll focus on yet another very interesting function of the parietal cell. What was the second important function of parietal cell? Intrinsic factor. Intrinsic factor. So author has given this diagram of what parietal cell, and author shows, look here, it is hydrochloric acid, and it gives rise to what? Intrinsic factor. Now this intrinsic factor is a large molecule. It's a glycoprotein. It's a glycoprotein, and before I go, this I am not going to teach you because I am inviting you to read this article. Beautiful article, only 2 pages, wonderful. Go to the website and read. What is the title of the article? Why doesn't what? Digestive acids corrode the stomach lining. Very interesting question. Okay, I am not going to teach in the class, but I will put a question. Very clear. That is my only method. Okay, to lead you into reading that article. So you have to read this article. Okay. Now, this intrinsic factor is another very interesting story in the digestion. So where do we go? We go to the synthesis of RBCs, which is happening where? In the bone marrow. Where is happening where? In the sternum, in the sternum and the long bones of your body. The bone marrow, RBC. Particularly for the when the DNA gives rise to protein and synthesis, you need two vitamins. If the 2 vitamins are not there, your bone marrow cannot make healthy RBCs. Very clear? Now, what are the 2 vitamins? One of them is a folic acid, which is called as what? Which is called as what? Also called folic acid, also called as what? And the B12, which is also called as what? Why is cobalamin called as that? Because at the center of this, you can see the cobalt there. Okay? And interestingly, you will find that this cobalt is also held in position by nitrogen, as in the case of hemoglobin. Good. So this vitamin B12 is very important. We get in the egg, we get it in the milk, okay, we get it in the fish, meat, everywhere. It's very commonly, it is very necessary, very sufficient amount of what? Both are essential for synthesis of DNA, particularly for the formation of what? Thymidine triphosphate, whatever, okay, and we need it for now when you undertake when you eat these vitamins as a part of regular food, okay, when we eat it, the chances are that they will be destroyed. At that pH, they will be destroyed. Okay, so the nature has to come up with a solution. Are you with me? And here is the solution. What is the solution? Intrinsic factor is the solution. So what it does is when you eat so what is this? What does this represent? It represents, say, vitamin B12. This in the stomach. So you have taken it as arrived in the stomach. It would normally be destroyed. It does not destroy because the parietal cell releases intrinsic factor, and the intrinsic factor combines, that molecule combines with vitamin B12, and as long as it is the 2 molecules are bound to one another, as if it has a security. Okay, it's protected. It can't be acted upon by the digestive enzymes. So what goes beyond in the duodenum is a combination of intrinsic factor plus vitamin B12, and then goes into the duodenum, and then it goes beyond duodenum into the early part of the intestine, and there the wall of the intestine pinocytotically taking the whole thing. Okay, it's a large molecule, it can't just diffuse. So the nature has come up with pinocytotic mechanism. Pinocytotically taking the entire combination of intrinsic factor and vitamin B12. Take it to the liver, process it, separate them, and store vitamin B12 and use it as and when necessary. Did you get the message now? So what have we done really? What have we done? We are trying to understand the profound importance of intrinsic factor, and it's a key factor in the absorption of the vitamin B12. Okay, what happens when you don't take vitamin B12? Okay, then you suffer from a condition which is called as a, can you read for me here? Megaloblastic anemia. Okay, because of course you don't have enough hemoglobin. Okay, but when you take a blood sample of a patient who has inadequate amount of B12 and therefore not able to synthesize enough hemoglobin, or the molecule is defective, the pathologist can easily make it out, because the RBCs which are so big, with a diameter of about 7 microns, they become so big. Okay, and also so can you see the two normal, that on the left is the control and on the right is what? An RBC of a patient. What patient? Megaloblastic anemia, and also even the WBCs. Okay, but they are large, but they are very inefficient. Okay, and therefore the person suffers from, and this disease is it's also an autoimmune disease. What do I mean by that? The person has antibodies, okay, against his or her own intrinsic factor, and as a result of that, intrinsic factor is not there. Okay, and then the person suffers from. What would be the treatment for this kind of scenario? You can't take a tablet of vitamin B12, but you can inject it. Hello, the solution is very simple. Okay, just take a shot. Okay, it directly goes. So the treatment relatively is very simple these days. You can just take a shot of vitamin B12 and then you are quite good about it. Okay, okay. Now I'll take you next step ahead, and we are looking at. Okay, now we are done with parietal cells. Any issues with the parietal cells? Anybody? Hello, are you okay? You okay there? Okay. So now let us talk about the enzymes being secreted in the stomach, and of course the number one candidate here is the pepsinogen, which is a source for the enzyme. Where do they come from? They come from chief cells. Where do they come from? Chief cells. Where are the chief cells? Chief cells are deep into the gastric pit. Okay, you have what you call as the chief cells, and here somewhere if you take a transverse section here, you have a lumen there of the gastric, that canal like which goes, and you take a section, and can you see here, that is a canal through which the fluids will flow, and on the periphery the author has shown a parietal cell and a chief cell. They are there in the, and little ahead you will also get H cells. Okay. So here we have, so what author has done is he has taken one chief cell from here and blow it up from there. We are looking at a single chief cell, and in the chief cell we have those huge vesicles, and they are of course containing enzymes, digestive enzymes, but all these digestive enzymes are at the moment inactive. They have to be inactive, they have to be activated a little later. Okay, and these vesicles are called as zymogen granules. What do you call them as? Zymogen granules. Here they are called as zymogen granules. Even in the pancreas, the pancreas will secrete different set of enzymes. We'll still call them as zymogen granules. So these are the zymogen granules, and when the cell is excited, it will release the zymogen granules, and then from the zymogen granules, the enzymes will come up. Okay, and it's actually not enzyme; it's a precursor of an enzyme. So what comes out is the molecule called as pepsinogen. What is the molecule? Pepsinogen. The molecule is called. Under the influence of acid, now it comes in contact with acid. Once it comes in the contact with acid, pepsinogen starts getting converted. Some of it gets converted into pepsin. Step number 1. Did I say? Pepsinogen. Under the influence of acid gets converted into pepsin. The bigger molecule is about 42,000 molecular weight. Okay, it becomes smaller. The pepsin itself is about 35,000 something molecular weight. So you have that pepsin. Now pepsin that is generated, it starts, now get the beauty. The pepsin that has been generated, that starts acting on the other pepsinogen molecules and convert them into pepsin. Beauty of the nature. Are you getting it? To begin with, you give a little acid and you start the process. So you have pepsin. That pepsin will act on other pepsinogen and give more pepsin. Okay, and then the pepsin will act on, and of course the pepsin needs strong, a very low pH, strong acidity, because that's the pH where the pepsin acts. So pepsin is an enzyme. Okay, pepsin is what is one of the three. Okay, one of the three principal protein degrading pepsin is of course in the stomach, and in the duodenum we will have chymotrypsin and trypsin. I will talk about it a little later. Regulation of pepsinogen is stimulation of the peptic cells by acetylcholine released by the vagus. Again same. You remember at the very beginning we made a statement. There are different secretions along the length of the alimentary canal, all different secretions. Most of them are, the secretions are stimulated by the parasympathetic nervous system, which mean by way of acetylcholine. Are you getting it? everywhere. So just now the parietal cell also responded, stimulated, the gastrin cell also stimulated, this chief cell is also being stimulated by the same. Yes.
The conversion of pepsinogen to pepsin,
Uh-huh.
is it also assisted by an enzyme, or it's like completely dependent on acid?
The answer to that question is acid can convert, but at very low efficiency. So when pepsinogen comes act and some of it cuts, but when even little pepsin is there, pepsin is efficiency 100, 200, I don't know, many fold, maybe 1000 fold, I don't exactly know, and then it rapidly converts epsin into pepsin. Okay. Now, so fill in the blank. Tell me the name of a hormone that is being secreted by the stomach. Gastrin. It should come instant, spontaneous. What is the answer? Gastrin. Okay. Now be ready for another shock. There is another hormone. Okay. And the another hormone is called as Ghrelin. Ghrelin. It's again a peptide hormone, 28 amino acids. Ghrelin comes from where? Ghrelin secreting cells. Where are the Ghrelin secreting cells? They are in the stomach. So can you see the first image and the image on the left, and can you see those gastric pits a little carefully? But can you see those black dots there? How did I get those black dots there, and what do they represent? They are what? They are gastrin secreting, they are Ghrelin secreting cells. How do I label them? By using antibodies against Ghrelin. Okay, so there is a stomach of rat. On the sections I put antibodies against Ghrelin and I get that color, so I can identify the Ghrelin secreting cells. Are you okay so far? Now this Ghrelin is a amazing, what is this? It's a hunger hormone. Nice to remember. Okay. So every time you have not had food for some time, and as a result of that the stomach is almost empty, and as a result mechanically the stomach becomes small, okay, small, Ghrelin cells are activated. What is activated? Ghrelin cells are activated. What do? They secrete Ghrelin. Okay, it's a peptide hormone, 28 amino acids. Where does the hormone go? Into the blood. It travels through the blood. Where? It goes to the brain, and it tells the brain what? That I am hungry. Okay. So how does, there are different mechanisms, there are different ways, but this is one of the very important ways of telling the brain, okay, and then in the brain generating the feeling of hunger. Okay. So then you trigger the behavior for search for the food and consume the food. Okay. So for initiating that behavior, one of the earliest cues, Q is Ghrelin. Okay. And so I think that is, the message is very clear here. Can you see the empty stomach versus the full stomach? When the stomach is empty, can you see the up arrow Ghrelin is equal to what? Up arrow what? Appetite, and then you have had your food, lunch, and then as a result of that the wall of the stomach are stretched. Okay, it's a mechanical signal. So you can ask another question: do Ghrelin secreting cells have mechanoreceptors? Okay, and under the influence of that mechanical stimulation, do they stop secreting Ghrelin? Because here because when the food is there, stomach becomes large. What is happening to the hunger? Goes down. What is happening to the appetite? It goes down. So an amazing phenomena.
Was it crossing the blood-brain barrier?
Which one?
Ghrelin.
That's a very interesting question. It's a peptide hormone. It's a relatively large hormone. Listen to this. It's a very fundamental question, and I'm giving you a complete answer. I'll ask you a counter question. Does insulin, so you have food, as a result of that beta cells secrete a lot of insulin, does that insulin go to the brain? I don't expect an answer, okay? Because you don't know the answer, I'll give it to you now. Okay. There are, very relevant question he has asked, very relevant question. What is it? Does it cross the blood-brain barrier? Look, every time everybody makes a statement that something is going to the brain and acting on it, you should first stand up and ask, does it cross the blood-brain barrier? period, that is it. Unless you get an answer to that question, do not go ahead. Does it cross the blood-brain barrier? Does it cross the blood-brain? A very pertinent question, very correct time. Does it cross the blood-brain barrier? Okay, so have I hammered on you the importance of that question? Good. Now let us see the answer. Whereas the capillaries in the brain have a barrier, here is the twist in the tail. It is there in the 99% of the capillaries of the brain. And what about the 1% capillaries in the brain? They are devoid of blood-brain barrier. And one of the places where they are devoid, they are called as circumventricular organ. And one of the very interesting circumventricular organ is present in the median eminence. I am going to, this word I am going to pronounce 10 times, median eminence. I am not going to pronounce it 10 times now, but I will pronounce the word when I talk about the control of the pituitary gland. Just above the pituitary gland at the base of the hypothalamus, there is a neural structure called as, say that again, median eminence, median eminence. Median eminence has capillaries where there is what? No blood-brain barrier. And it is through this blood-brain barrier that these hormones like insulin, leptin and ghrelin get in from the blood and directly have access to the neurons. So, the brain on one hand, it has taken steps to protect itself by inserting a blood-brain barrier. Where it is necessary, it says, okay, I do not care, I do not need that. But that is only in few places. And one very important place I told you just now, what is it? Median eminence. Have I answered your question, gentlemen? Okay, remember that is very, it is good you asked, median eminence. It is one of the, you know how it happened? You should have not asked that question, then I will stop this and talk only about that. You know how blood-brain barrier was discovered? The story goes to about 1934, when they injected a dye like methyl blue and methyl green and methyl whatnot, and they injected the rat, and they took out the brain, and they took out all the organs. So, muscle stained, liver stained, pancreas stained. Brain white. Brain was white. So, my dye which I inject intravenously route, if it goes everywhere, why does not it go to the brain? There must be something, blood-brain barrier was discovered. But when you look at the brain carefully, you find that median eminence is stained. Got the beauty of the situation? And therefore, they knew that, well, blood-brain barrier is everywhere, but 99%. Places like median eminence, and there are a couple of more places, organum vasculosum, do not bother about it, organism vasculum, I will tell you, organum vasculosum lamina terminalis. You remember something? No, I think I should tell it to you. You remember we talked about the osmoreceptors. Osmoreceptors, in strict sense, the cells of the OVLT are osmoreceptors. Are what? Enough of neurobiology. So, here we have, okay. So, we are measuring the, you keep on drawing the blood, a human, okay, and keep on monitoring over a period of entire day, and you find that this is the ghrelin, profile of ghrelin, and what is this point? Breakfast. Okay, so at this point, so he is hungry, has breakfast, goes down. Are you with me? Hungry, has lunch. So there is a very clear correlation between what and what? Hunger, take in food, hunger, ghrelin. Okay, and you have food, and the ghrelin level goes down. Okay, we will move on now, and talking about what? Talking about pancreas. Okay, so here is the beautiful organ. There are like the salivary gland, there are acini, the single layer of cells, and there is a duct there. Okay, and there are this is the entire organ, and the contents are poured into the duct. The hundreds of them, they all pool together. So this is a single acinus, and these are the cells, and it's rich with endoplasmic rough endoplasmic reticulum, which means that it is a protein synthesizing cell, and then it also has and this histological section you can see the acini, and I put this section because these are all the acini, and that you can clearly see what islet of Langerhans. So, these are the cells which are pancreatic cells. If they are the exocrine cells, endocrine cells, and the exocrine cells are responsible for. So, these are again you can see the can you again see the zymogen granules there? Okay. What do they contain? They will contain the enzymes. Okay, and what are the enzymes they contain? They contain okay. Oh yeah, let me give a correction there. Our call site is we call them as proenzymes. Makes sense, okay, because they are inactive. Okay. You know what? There is a disease in which that duct, you know, that we saw in the previous one, that duct gets clogged, and then this enzyme, I am sorry, this inactive enzyme, okay, is not able to flow, and then if we obstruct it, then for some reason we still do not know, the enzyme gets activated, and if the enzyme gets activated, the enzymes eat up the pancreas. Very dangerous situation. Are you with me? The enzymes, so, and it is called as acute pancreatitis. Acute pancreatitis. Are you getting the meaning? Okay, and it is absolutely fatal. It is very difficult if the pancreatic enzymes are activated. Okay, when they are still in the pancreas. Well, you can imagine they are extremely powerful enzymes. So, this is the electron photomicrograph. You can see the zymogen granules, that is a diagrammatic, and they are huge containing. They are containing the enzymes like chymotrypsin, chymotrypsin. And so, what are the three enzymes that you are going to get? The trypsinogen means what? Prohormone, trypsinogen. You can also call it chymotrypsinogen and what? Carboxypolypeptide, whatever. These are the prohormones will be released when the pancreas is stimulated. How it is stimulated, I will tell you very shortly. And this then, after that, trypsin and so lot of proteins are already digested, okay, and they are broken into smaller molecules. Okay, they are further acted upon by the chymotrypsin and the other one and the trypsin, okay, so that you have, get the point, dipeptides and tripeptides means what? Tiny fragments. See, what the proteins we use are huge molecules. Okay, they are broken down. Our ultimate aim is to bring it to single amino acid. Okay, so that it can be absorbed. Okay, so whereas can somebody read for me what is written in the blue font? Read loudly. Trypsin and chymotrypsin split whole and partially digested proteins into peptides of various sizes, but do not cause the release of individual amino acids. However, read the last part. However, carboxypolypeptidase does split some peptides into individual amino acids. Okay, so these and please remember, this is oversimplification. There could be half a dozen different trypsins with a little difference in amino acid here and there. Okay, and the release of that could depend on the type of food you are eating. Okay, we are generally lumping them into one, but the life is not so simple. Okay, now this is interesting. Just follow the story. We are looking at the wall of the duodenum and the intestine, innermost wall, the mucosa. Okay, and sitting on the mucosa, there is an interesting enzyme. Can you please read for me the name of that enzyme? Enterokinase. What do you call it as? Say that again. It's just sitting there on the top. Just look at it's just on the top. The enterokinase is sitting there. Now, what does enterokinase do is trypsin. Okay, means what? Trypsinogen. Okay, trypsinogen can be converted into trypsin. How that happens? Let's see. The trypsinogen is coming. Where is this coming from? Is coming from pancreatic cells. Where? Into the lumen of the duodenum. Okay, so far this trypsinogen is being acted upon by what? Enterokinase. What is the net product? Trypsin. And once trypsin is there, it acts on further trypsinogen to give rise to trypsin, something like pepsin. You know, the pepsinogen was converted first initially by the effect of the acid into pepsin. A very similar phenomena is happening here also. So, trypsinogen to initiate the first push is given by enterokinase. So, once the enterokinase acts upon trypsinogen, you get trypsin. Once the trypsin is available, the guy takes over the entire job, and then trypsin converts chymotrypsin into chymotrypsinogen into chymotrypsin active enzyme, and trypsinogen into trypsin, okay, and now these enzymes are available there. So, but this enterokinase has a very interesting role to perform. Did you observe the point, everybody? Great. So, we will talk about, so here we have the, this is what I was talking about, pancreatitis. Here is actually an example of that. I said the pancreatic, okay, let us see. So, here is a common duct. This is a part of the duodenum, here is a common duct. What is the duct bringing? It is bringing bile, and it is all bringing pancreatic juice. Common duct releases its content into the duodenum. Now, bile has a habit of forming stones, okay, and you may be surprised to know that even several of us might have stones in our gallbladder. Normally, they do not bother you, okay, so we do not worry about it, okay. They could be there, they could be there. Supposing they start getting bigger and then they flow along, and that is where they go and sit at the mouth of the tube. Papilla of Vater it is called as, but do not bother about the name. That is where they sit, and if they sit there, then the pancreatic juice cannot go into the stomach. So, pancreatic juice accumulates. Means what? You have taken food, the food has gone from the stomach into the duodenum, the signal has gone to the pancreas to that you keep on pumping, secreting lot of pancreatic juice, but pancreatic juice cannot find its way into duodenum, it gets stuck there. Once it is stuck there, we do not know why all the enzymes could get activated. How, we still do not know. And as a result of that, you could have this entire organ being eaten up, and the condition is called as what? Pancreatitis. Okay, very dangerous situation. I think I will stop now.